Great. Thank you for the introduction and also for the organizers to giving me the opportunity to talk here in this audience. Yes, the title of today's presentation is Characterizing and Optimizing Next Generation Solar Cells. And this is work done mainly by the co-authors listed here that are either from Fluxim or from ZHAW. So let me first introduce so people behind the Organic Electronics Photovoltaics and Terahertz Photonics is a research group which has 4 teams at Zurich University of Applied Science. And later today, my colleague Evelyn Knapp will present her work on machine learning. So she's more the expert on machine learning. And the other teams here do work on OLEDs, perovskite solar cells, and so on. And the company Fluxim was actually founded in 2006. And over the years, we have established several R&D tools. The initial product was ZFOS simulation tool for solar cells and OLEDs. Later on, a second simulation tool, LAOS, was released for large area cell simulations. But we also have measurement equipment, PIOS, PHALOS, LITOS Light. So these are equipments that may appear during the presentation. I hope you don't mind. So let me just introduce a bit. There are different kinds of research approaches. This conference is about machine learning and high throughput experimentation. Let's keep in mind that different characters in research also have different preferences how to do research. Some want to do purely simulation of devices, virtual devices. Others want to study maybe just a single device in very much detail, doing lots of experiments and extracting parameters. Then once you scale up the cells from cell to module size, you need to care about the layout, and you need to design the mini module. And of course, other people care more about stability and lifetime data. And the more cells fabricated, the more data will be collected. And finally, machine learning is also a popular topic these days. But which of these methods can maybe be combined in order to take best benefit of several approaches? So let me start out with high throughput measurement systems. So you know that traditional way of characterizing solar cells is just take a JV curve, which you can do with a source measure unit, and you may just hook up one cell. But then there are more interesting measurement techniques that can provide more information, like pulsed techniques. And the instrument that we have proposed the last 10 years and commercialized it actually includes many different measurement techniques, from JV to transient and also to the frequency domain, impedance spectroscopy, for instance. So this is about on the order of 1,000 measurement techniques, and then you can hook up one cell or up to 4 cells. But if you want to have more statistics, you could use as an instrument LITOS we designed to have 32 channels split in 4 measurement chambers at different temperatures. And of course, you can also then combine measurement techniques for characterization with this high throughput 32 cell characterization. And a third dimension would be the time or stressing time, which is not displayed here on the graph, which then would give even more data if you repeat the measurement techniques and stressing at different cells. And finally, we also introduced 56-channel solar cell measurement platform where you put the sample holder below a solar simulator. But of course, the question is how much data you want to generate, how many samples you want to characterize. In the extreme case, if you're interested in physics, you may end up just using one sample, but many measurement techniques and try to understand one representative sample. So we typically propose to not analyze too many samples at the same time, because otherwise you're just drowning in lots of interesting data. But to illustrate a bit the dozen measurement techniques that we provide with the PIOS instrument, we have here an overview of JV curve, transient EL, transient photocurrent signals, impedance spectroscopy, IMPS, IMVS. So this already provides lots of data, even just for one solar cell. So in that sense, it's a high throughput measurement system. But once you have acquired all this data, the question is how to analyze it. And one way to do this is to use simple formulas to do JV curve fits or equivalent circuit fitting, or extracting mobility from rise times of EL or also photoCLIF. But alternatively to this kind of basic prose processing, we also try to promote the use of drift diffusion modeling, where you actually have electron hole semiconductor picture of the device. So once you fit the JV curve, and in this case capacitance frequency data of a PIP device here with 3 different thicknesses, you actually can dive into the cross-section of the device. And here you see the steady state charge distribution in this PIP device and given voltage offset. And also corresponding to this frequency sweep, you get the frequency dependent charge oscillation here, cross-section of the device. And this allows you to understand why you have a low frequency capacitance rise. That basically means you're penetrating your oscillation of charge carriers more deeply into the device compared to more medium frequency range here. So these are the basic processes, basic cross processing and also simulation-based material parameter extraction. And in order to do this kind of parameter extraction in terms of fitting, let me make some comments about fitting. Once you measure the data, what you can then do is set for simulation with drift diffusion, and we call this set for bias integration. You can call the simulation from the measurement control software. The other way around, you can actually also import any kind of measured data into the simulation software and try to fit the data there. But some general comments about fitting. What do we mean with fitting? We mean we want to minimize the error between the experimental data and the simulated data. And if this error is minimized, then we are happy with the fit, and we can take the model parameters as extracted parameters. So this is actually an optimization problem where we minimize the error between experiment and simulation. Now, how to do that? Manual parameter adjustment is always an option. Some experienced people are good at that. But then there are also, of course, algorithms to do this. Either you do a local optimization, and the popular method that we implemented is Levenberg-Marquardt algorithm to minimize the error. But keep in mind that the error landscape, here an example with 2 variables, might have multiple local optima, and a gradient best method may be trapped in a local optimum. So this is why we also propose to use global optimization algorithms. And here I am mentioning today simulated annealing and Bayesian optimization as 2 powerful methods that we implemented in our simulation tools. And yeah, of course, they have also some issues. Sometimes you should care also about correlations, and to characterize that, especially the gradient-based methods allow to use the Jacobians in order to calculate the correlations between the best fit model parameters. But let me illustrate the simulated annealing and Bayesian optimization algorithm for this tandem device. This is a perovskite silicon tandem cell structure where we have the perovskite thin film deposited on the silicon wafer, and this is not to scale. The silicon wafer is 280 microns thick down here, and the thin film coating of perovskite is on top. And the 2 parameters we are interested, so there actually we have 5 parameters that we are allowed to vary in the optimization, but let's look at 2 parameters, namely this anti-reflection coating layer, magnesium fluoride, and the perovskite active layer thickness. And if you plot the current of this tandem, it's a monolithic tandem, so the software should also take care of the current matching. And this actually leads to a very strange landscape of current, where you don't have edges that are not differentiable. So this also calls for specific optimization algorithms. And Now, the result for simulated annealing and Bayesian optimization is shown here. On the left, we see that the simulated annealing method, yeah, it is able to identify the optimum combination of magnesium fluoride thickness and perovskite thickness. But you see that there are many random kind of evaluations where this optical tandem calculation has been repeated. And the Bayesian optimization actually is an elegant approach which is based on a surrogate model that is being updated whenever you add another evaluation point. The surrogate model is getting better and better, which allows the algorithm to quickly find the global optimum. And in this case, the Bayesian optimization is a faster algorithm which has used less number of evaluations. So this is illustrating that there are different optimization algorithms available. Some time back, more than 10 years ago, when we started with OPV modeling, we established the thin film optics light penetration calculation shown here on the left, and then the photon absorbed are then coupling into the drift diffusion model by this term here in the exciton rate equation. And then there is charge transfer exciton dissociation that gives free carriers that are then extracted or maybe also recombining. So this is an introduction to drift diffusion modeling, and at that time we received solar cells from the TU Eindhoven group. They've manually made spin-coated OPVs with different thicknesses. You see the black dots are the measurement points, and the simulation result of the optoelectronic simulation is the line that fits here. That's the first example. And now just recently, or let's say 10 years later, some research group in KAUST, they also did a similar thing. They tried in a first step to fit the measured data of this bulk heterojunction OPV with a non-fullerene OPV with a rather high efficiency of more than 17%. And you see in a first step, you can reproduce the measured data, but then as an additional thing, you can also artificially vary the material property, in this case, the donor band gap, as shown here with the extinction spectrum, which was artificially shifted in order to see whether we get a higher power conversion efficiency. And indeed, you see that there's a local maximum somewhere here. And this virtual optimization, after having a model calibrated, then varying the model parameters in order to get a better performance, that can be done more in terms of mobility variation, thickness variation, and band gap variation. So this was drift diffusion modeling of an OPV with free carriers. But then once the perovskite solar cells became popular, we also needed to adjust the model and extend it by implementing anions and cations in the perovskite active layer. And then this allowed us to reproduce measurements that were done for different preconditionings with pious JV curves that were measured. We were able to reproduce them with the help of ions that are also redistributing in the preconditioning at 0 volt and 1 volt. And this kind of mixed electronic ionic model allowed us also to reproduce a range of measurement techniques for this perovskite solar cell. You see JV curves, you see pulsed experiments, you also see frequency domain experiments like capacitance frequency down here and IMPS over here. And this, after such a successful fit, then you actually have material parameters extracted. But sometimes it's also interesting to compare two different cells. In one cell, passivation layer was omitted in order to actually control the recombination at the surface of the perovskite film. So in the measurement, we see the regular solar cell that gives, after some delay time, there's a quick rise of the current. This is a response to a voltage step. And if we remove the passivation layer, then the voltage step is more smoothened and the rise to the DC current is much slower. that indicates that there has been some strong recombination at the surface, which then was also reproduced by the model. So sometimes you can also understand more what's going on in the different cell types. Okay, then I will continue here. I was introducing the distribution modeling for OPVs, with free carriers, and then switching to mixed ionic and electronic modeling of perovskite solar cells. This is needed in order to reproduce JV curves at different preconditionings, as shown here. And in the model, we can also do the same preconditioning and get the good JV or the S-shaped JV. Now, some years ago, we also introduced a global fit for this kind of perovskite solar cells by reproducing JV curves and pulse data and frequency-dependent data, as shown on the bottom here. And we also compared two solar cells, one with and one without the passivation layer, for which the voltage step experiment exhibited a slower rise in case of no passivation layer and a fast rise in the case of with passivation layer. And this qualitative behavior was reproduced in the model also by introducing more surface recombination for the solar cell without the passivation layer. I introduced that the parameter correlation should be taken care of, because modeling JV curves, for instance, alone, that's not good enough. That leads to a model parameters that are strongly correlated, as you can see by the coefficients here that are close to 1. But if you analyze in a global fashion multiple measurement techniques like in the example shown here, then you can reproduce the correlations as shown in this example, which was published a couple of years ago for an OPV that was measured with many techniques and also fitted with drift diffusion. Also, an OPV case study we published this year. It's an OPV tandem with two subcells in monolithic fashion. And here we just reproduced a published data set from another group, and they measured subcells and also the tandem. And the lines are our model. And the idea then, after calibrating the model this way, we were interested to see if there are even better combination of layer thicknesses that give a better performance. And this you can do either by doing just optical stack optimization, and we got an optimum for this thickness combination, or you can do full optoelectronic device simulation and get another optimum with a slightly higher power conversion efficiency. And further details of this study are in this publication down here. The recent couple of years, we also did work on perovskite silicon tandem solar cell modeling. And in that case, you have the perovskite as a top cell, and you care about the charge recombination interface. If this interface is not optimal, then you will have a voltage loss, and you would see that in the VOC not being the sum of the VOC of the subcells. And with the drift diffusion model, you can make cross sections of the currents that are generated and also the recombination interface to study more what's going on. But now I'm switching back to optical tandem calculation, especially for these high efficiency tandems approaching 30% PCE. They have to exploit light scattering. And this is also done with our software here, where we introduce textures for light scattering, which allows us to go from a more oscillating EQE at giving low photocurrent to a more flat EQE spectrum with a higher photocurrent. And you can do also model validation. This was a few years ago, a tandem device fabricated at PV Lab in Neuchâtel, and the measured data of the EQEs here of the two subcells were reproduced with our simulation. For the planar case, that's the structure A, you see there's a lot of reflection losses, and the reflection losses can be somewhat reduced by introducing an anti-reflection coating or scattering of on the rear side of the wafer. And you can further play around by switching from NIP to PIN structures, for instance, by adding anti-reflections, and also do a fully textured front and back side silicon wafer And this would allow you to go from this kind of EQE to the more flat and high efficiency EQE spectrum. But now I'm trying to speed up and go to the last part of my talk, which is about Larissa, who would like to do scaling up of cells to modules. As you know, there are some, for any PV technology, this quite often happens, a loss in the efficiency PCE as you go from small scale to large scale. And for that challenge, we introduce software for large area modeling. It's a FEM-based software where we solve the Ohm's law in the top electrode and the bottom electrode, and we do a coupling of the top and bottom electrode by introducing a JV law. So either we do this in steady state, it gives us the electric potential distribution in the solar cell and would also allow us to calculate an EL image and also the JV curve here in steady state. But more recently, okay, now this steady state example, what you can do with it, you can calculate a mini module. This is an OPV mini module of the Greek company OET. You see the interconnections and also metal grid lines in order to improve current collection. And then here the cross section of the P1, P2, P3. And with the software, we can optimize the number of subcells serially connected and also optimize the grid line layout. But then recently we also established a frequency domain large area solar cell model, and further details are in this publication down here from last year. It's basically using the same concept of two electrodes coupled with a vertical coupling law, but instead of solving the equation in the steady state, we go to frequency domain. We use small amplitude modulation around voltage offset, and this allows us to then calculate AC response electrically and also thermally. And I'm giving you some examples. So in the steady state approach, we calculate JV curves and EL images or steady state IR images. But in the frequency domain, we can calculate impedance spectroscopy data and also SST leads. And I show you here some examples. JV curves, of course, we play around with sheet resistances and adding or not adding a metal grid to the mini module. And then the new model for AC electrical model allows you to do impedance arc calculations for different layouts of the solar cell, or simply also varying sheet resistance would give you a different size of these arcs. And remember, this is not a 1D model, this is really a large area model, which then would be sensitive to any sheet property and layout, or also a local shunt that would modify the impedance response. In terms of IR imaging, there is the classical steady state images that are actually, however, very blurry. So this is a mini module for OPV module cells in series and measurement and simulation. This is for the mini module shown here, CSM, but now in the frequency domain and the so-called lock-in thermography technique, you see that we can get more resolution of the images. We get an amplitude and a phase image, and this is actually providing more information. And thanks to the model that we can now solve in the AC domain, we can also generate images of amplitude and phases. And this is shown for this perovskite solar cell example, which is a perovskite solar cell provided by Solaronics. In that case, this is about 1 centimeter square size perovskite solar cell, for which we measure the EL down here, and also the simulated EL picture. And we introduced a little shunt here that you can hardly see in the model. And how do we do that? We basically modify the coupling law at this local position. We introduce a more conductive shunt property, which then gives rise to a local point here. And in the frequency domain, we again see amplitude images for different offset voltages. And you see that some defects are visible always, but if you increase the bias, then we also have some influence of heating due to current collection at the boundary of this square cell. Now the model description for 0.9 and 1.6 volts shown here. we see the shunt, how it behaves, and also the shunt plus the heating at the boundary can be quite well reproduced qualitatively and quantitatively. So with this, I'm going to conclude. It's Christmas soon, so let me say that different researchers have opportunity to use different tools for simulation, for detailed parameter extraction with instruments, and also for scaling up. And the other topics of stability, and I did not touch today because of lack of time. I hope I didn't consume too much time and could catch up some of it. So I conclude with thanking my team at Fluxim and the people that were mainly involved in these case studies. And also, as a summary, show you a graphical summary of this presentation. I started out with cell simulation and optimization algorithms. I gave you some examples about perovskite characterization, so cell characterization in different time and frequency domain, and then went to tandem optimization, and which finally to the scaled up devices where we can do impedance or also imaging characterization. So thank you for your attention.